Hello again. We start with the third section of this chapter, in which we focus mainly on the applications of mechanical energy and how are we able to use the equations that we acquired in the previous two sessions in order to solve some problems and applications. First, let's check the objectives again of this chapter, in which we defined work and we also recognized potential and kinetic energy along with mechanical energy. Now we're going to go to apply the principle of conservation of mechanical energy. Also with the chapter plan, we have finished the first 5 sections. Now we're going to focus mainly on these two, 1.6 and 1.7. The first concept we're going to talk about is conservation of mechanical energy. First, the term conservation means something is being constant. Being conserved means it remains of the same magnitude or value. When frictional forces, chemical or nuclear reactions do not exist, mechanical energy is conserved. This is known as the principle of conservation of mechanical energy. Now, to express this mathematically, we say ME initial, mechanical energy initial, equals mechanical energy final. In order to use this in problem solving, it's essential to specify what system you're studying and which instance or situations are you going to consider as initial and final. Observe the figure here in which we have a boy carrying a marble. Now, as the boy carries the marble above ground, therefore, the marble and earth as a system together possess gravitational potential energy. So at that instant, energy is purely gravitational. Notice. Then, as the boy releases the ball, GPE decreases while kinetic energy starts increasing. Once the ball reaches the ground, all it possesses is kinetic energy. Over here, it's important to mention something very remarkable in this animation. The ball was moving all the way slowly. This is done just for the purpose of explanation. In fact, as the ball drops, it moves much faster. The second point, which is worth mentioning, is that when the ball reaches the lowest point with only kinetic energy, it possesses some speed. Therefore, it should bounce off the floor or the ground. Nevertheless, for the purpose of explanation, we assume that we have frozen the picture once the ball reaches the ground. But when it reaches the ground, it definitely has some speed and some kinetic energy. Another remarkable thing is, if you remember, the GPE graph was over here, and once the ball reaches the ground, its kinetic energy reaches the same level. This is again the concept of conservation, because when it was on the top, energy was purely gravitational. Once it drops to the bottom, all gravitational potential energy transformed into kinetic energy, keeping the sum, mechanical energy, constant. So delta ME equals to 0. That's how we write these things mathematical, meaning delta ME, which is delta KE plus delta GPE. Now solving some mathematics, we notice this sentence here. Yes, it's a sentence. It's a mathematical statement. Delta K equals minus GPE, meaning in any system when mechanical energy is conserved, meaning no frictional forces or chemical reactions involved, the variation of kinetic energy is opposite to the variation of gravitational potential energy. If one increases, the other should decrease, and vice versa. Okay, and this is stated over here. The variation of kinetic energy is opposite to the variation of gravitational potential energy. Concept 1 is done. Let's move to the second one. Non-conservation of mechanical energy. Opposite to what we have discussed before, in presence of frictional forces, resistance, or chemical reactions, here or can be with chemical reactions only, or friction and chemical reactions. Mechanical energy is not conserved. It's not conserved. That means mechanical energy initial is not equal to the final. Going back to our boy here, at this point, energy is pure gravitational. Notice the level that we talked about before. Now, when the ball is going to be dropped, it will move down, acquiring some kinetic energy. When it reaches the bottom, we're going to freeze the picture and consider kinetic energy at that point only. Notice as it reaches down in slow motion, once it reaches the floor or the ground, the level of kinetic energy is below the gravitational potential energy. That means some of the gravitational potential energy was converted to kinetic and the other is simply lost. In case of resistive forces, such as, let's say, friction, mechanical energy decreases. The loss in mechanical energy is transformed into thermal energy or heat. Sometimes it's transformed into vibration, into sound, and stuff like that. Nevertheless, for the time being, we just stick to the idea of energy being lost as thermal energy or heat. Delta mechanical energy, the variation of mechanical energy, is equal to the work of that friction. This is a remarkable thing, and it can help us relate loss in mechanical energy into the work done by the frictional forces. If you ever wonder where does that energy go, simply it goes as internal energy. Now, how does it appear or how is it transformed to the internal energy? The work done by frictional forces takes that energy, applies some F times D, and that energy is transformed to the inner part of the system as internal energy. In this scenario, mechanical energy decreases. On the other hand, internal energy increases. Mechanical energy decreases, internal energy increases. On the other hand, if the forces are motive, such as traction of a car, for example, mechanical energy increases. Again, the increase in mechanical energy is equal to the loss in internal energy. These are just conceptual ideas that I would like you to know. When it comes to calculations and problem solving, situations are going to be much simpler. Okay, that's all concerning this chapter. In the upcoming session, we're going to talk more about applications. In fact, all that we're going to do is just solve applications. One more application that I would like you to solve to check that the conservation of mechanical energy concept and non-conservation concept are both acquired well and properly. This is application 4. Read it in part 1, in phase 1, and in part 2 or phase 2. Try to solve it, and in the upcoming session, you're going to have a full description and discussion of all the problems and applications that we have mentioned. That's all concerning this session. One more note before we leave. If you remember at the beginning of the chapter, we talked about a rocket being launched to space. That rocket, if you remember, loses internal energy because it's burning some fuel. That internal energy which is lost is converted into kinetic and gravitational potential energies, which we can call now mechanical energy. So this is a direct application of what we have talked about. Thank you for your time. This is all concerning the chapter. Go over all the equations and the concepts that we have discussed, solve the applications, and in the last session, you will find detailed solution of all of them.